Okay, hello, welcome to our face-to-face meeting for Stat 151 today. We are going to talk about section 3.1, which introduces continuous random variables, or as it calls it, random variables of the continuous type, I guess. What I'm going to start with is just a little sort of overview of some of the topics in this section. I'm going to work through an example that touches on a lot of those topics, and then I'm going to answer a few questions from the discussion board about the homework assignment that's due on Friday. Okay. So when we worked with discrete random variables, we worked with probability mass functions. We call those little f of x, and we use them to find the probability that x takes on exactly a particular value, little x. When we work with continuous random variables, we're going to work with a different kind of function called the probability density function, and we call that a PDF for short. We still use the notation little f of x, and the PDF needs to be an integrable function, and it has to have the following characteristics. The first one is that it always has to take on values greater than or equal to 0 for all values of x that are in the support of our random variable. So remember, the support is just all the sort of possible values that x might take. B, next condition, is that if we integrate the probability density function f of x over the entire support of x, that the total area under the probability density function has to be equal to 1. And then the third condition is just to kind of going to focus on how we define probability using probability density functions. And if the interval from a to b is a subset of the support, then we can find the probability that our random variable x takes on a value that's between a and b by integrating from a to b our probability density function f of x with respect to x. So when we're finding probabilities with a probability density function, f of x is not going to be used to calculate the probability that x is equal to some particular value. That was true in the with the probability mass functions in the discrete case, but this is not true in continuous random variable situations. And we'll see why in a minute. So instead, the idea with the probability density function is we're going to use area under the curve in order to find probabilities. So the other thing, just kind of extending some of the things we talked about before, we used the term cumulative distribution function. We called that the CDF before, and that we used the notation capital F of x and could use it to find the probability that our random variable took on a value less than or equal to our particular value little x. We do have this same idea of a cumulative distribution function with continuous random variables, but in order to find it, the way that we find it is we integrate from the smallest value in the support. I'm going to put negative infinity in there, but really it's whatever the smallest value in the support is, up through our x value. We integrate our probability density function, little f of x, with respect to x, and that is going to give us the value of f of x. Let's see. Other things, mean and the variance. We still have the same ideas. The mean, which is the expected value of x, when we calculate expected values in the continuous setting, instead of adding with a summation our x times the probability that x takes on that value, we're integrating x times the probability density function x of x with respect to x, and evaluating it over the entire support of x. The variance of x still has the same definition, that it's the expected value of x minus the mean squared. When we write this, we can think of integrating again over the support of x minus the mean squared times f of x with respect to x. This is the same idea as we had before. We're taking the x minus the mean squared and multiplying by the probability mass function, except now we're multiplying by the probability density function, and instead of summing, because we don't have a discrete set of possible values in the support, we are integrating. But otherwise, very similar definition. And just as a note, the formula, the sort of shortcut formula, the variance of x is equal to the expected value of x squared minus the mean squared. This is still true. So we could focus on the expected value of x squared, calculating the expected value of x squared instead of doing the integrating with the subtraction in here. I guess the last sort of topic I just wanted to mention is this idea that we haven't talked about before, which is percentiles. The pth percentile is really the set of all values of x, so that the probability that our random variable takes on a value that's less than or equal to our x is equal to p. So what this really means, if we think about it, is that it's the set of values for which p percent of the distribution is less than x. So you've probably heard the terminology percentiles before in other places, maybe in Stat 141 or Stat 111. And this is the same concept. It's, think about the percent of the, we're looking at a distribution of data, we say the pth percentile is the place where we have p% of the data are below that value. Here we have p% of the total probability is less than the value x. Okay, so just to illustrate these ideas, I want to do one sort of example kind of all the way through. So I have a cumulative distribution function, f of x. It's 2 over 49 times x for x from 0 to 7, and it's equal to 0 elsewhere. So I've graphed my probability density function f of x over here. Now, if I want to find the cumulative distribution function, I'm going to take my probability density function, 2 over 49x. I'm going to integrate with respect to x, and I'm going to, actually, let me just write that slightly differently, because I'm going to integrate from my smallest possible value in the support, so from 0 up to x, and also I'll just integrate with respect to t. So I'm writing my probability density function with a t in place of the x and integrating with respect to t, just to make my notation a little less confusing later on when I start substituting x in there. So this is going to give me t squared over 49. And I'm going to evaluate it, which gives me x squared over 49 as my cumulative distribution function. So for any value x, if I want to find the probability that my random variable takes on a value less than or equal to x, that's my cumulative distribution, f of x. Really, it's going to be, if I'm, for values that are less than 0, it's going to be 0 when x is less than or equal to 0. Then it's going to be given by x squared over 49 when 0 is less than x and x is less than 7. And it's going to be equal to 1 for values of x that are greater than or equal to 7. Because I know that the total probability that my random variable takes on a value less than 7 is going to have to be equal to 1. Because it can't take on any values larger. And similarly, it can't take any values less than 0, so the probability that it takes on a value less than some number that's less than 0 is also going to be 0, which is how I got this first condition. Okay, so there's my cumulative distribution function. If I want to find the probability that x is equal to 3. Now, often people will make the mistake of saying, oh, I'll calculate f of 3. That would not be correct. Okay? The probability density function evaluated 3 only is going to tell us the height of the PDF at that value. It's not the probability. To find the probability, I would have to integrate essentially from 3 to 3, right? This probability density function, 2 over 49 to the x power, which is going to give me a value of 0. So this is comes back to the idea we had way back in the very first section of the book. It asks us to sort of intuitively think about if we had something that could take on any value in a continuum, what's the chance it would take on a value of exactly a particular number? And because of the fact that we have this uncountably infinite number of possible values in this range, the probability that it takes on any one of them is 0. And so when we have a continuous random variable, one very important thing to remember is the probability that x is going to take on any specific value is always going to be 0. Okay. And I mean this as an exclamation point, not as a factorial. Not that it would be, but 0 factorial would be 1, so that's a 0. We'll put like a couple of exclamation points so we understand. Okay. Let's see. On the other hand, if we want to talk about finding probabilities, we have to think about finding probabilities that x is in a particular range, because probabilities correspond to areas under the curve. So if I looked, say, at 3, there's no area associated here because there's no width. But if I want to look in a range, say from 2.9 up to 3.1, the area under the curve in that range is going to represent the probability. And the way that I calculated that is going to be by integrating from 2.9 to 3.1 my probability density function, 2 over 49 times x dx, which is going to give me 3.1 squared over 49 minus 2.9 squared over 49, which is approximately 0.025. So just in terms of finding areas, we're going to integrate. If I want to find the probability that x is less than 3, x is less than 3 here, I can think about looking here from 3 and less, so down here. So I need to find this entire area from 3 and down below. So I'd integrate from 0, where my support really begins, up to 3, my PDF. Which is going to give me 9 over 49 minus 0. And it gives me approximately 0.184 for the probability that x is less than 3. The probability that x is less than or equal to 3 is going to be the probability that x is less than 3 plus the probability that x is equal to 3. The probability that x is equal to 3 is 0, right? So this is equal to the probability that x is less than 3. So I mention this specifically because sometimes people aren't sure. Does it matter if I have a less than or equal to or a less than? When we're working in the continuous case, because the probability of x taking on any exact value is 0, the probability that x is less than or equal to 3 is the same as the probability that x is less than 3. And the probability that x is greater than or equal to 4 is going to be the same as the probability that x is greater than 4. So just to kind of keep in mind that we could write that either way and the probabilities will be the same. When we find the expected value of x, again, what we want to do is we're going to integrate over the entire support. So here we're going to go from 0 to 7. We're going to take x times f of x. So that's going to be from 0 to 7. We're going to have, let's see, 2x times another x would be 2x squared over 49 dx. When we integrate this, we'll get 2 over 147x cubed from 0 to 7, and that's going to give us 14 thirds. So that would be our expected value. So just integrating x times f of x. And for the variance, the easiest way is to use the computational formula. We already have the mean here. So the expected value of x squared minus the mean squared. So then I need the expected value of x squared, which is going to be the integral over the whole support, 0 to 7, of x squared times f of x. That'll give me the integral from 0 to 7 of 2x cubed over 49. If we complete the integral and do the evaluation, we should get 49 over 2. And then we can use that here and say, okay, the variance is going to be 49 divided by 2 minus 14 thirds squared. And then the last thing I want to look at is just when we want to find the percentile. The book used the notation Q1, the first quartile, and it should be, sorry, it should be not here, but here. And they use this pi notation to mean it's the percentile where we'll have 0.25 as the probability that x is less. So we're looking for the spot where the probability that x is less than or equal to little x is equal to 0.25, which means that, remember, this probability that x is less than or equal to x is our cumulative distribution function, capital F of x, has to be equal to 0.25. And that is going to be, since we found the cumulative distribution function up top, which was x squared over 49, means that x squared over 49 must equal 0.25. And we can solve this for x and find that x is equal to 3.5. So this would be our first quartile, or pi 0.25, the 25th percentile. Okay. So let's just sort of go through one long example. Notice that I did use calculus to solve these problems, but I actually could have found areas in other ways, right? If I were looking for the area, the probability that x is less than or equal to 3, I could have figured out the area of this triangle using geometry also. So sometimes you don't always need to actually do calculus, but you need to find area. The main thing is to understand that what we're really looking for to calculate probabilities is the area under the probability density function. Zach?
Will the single quartile always be equal to a quarter of the expected of x?
No, it won't always. No, it will not. That's just a kind of a coincidence. Well, and
Since it's linear.
It's because it's linear, exactly. Okay. All right, so that was, as I say, just an example, hopefully to help clarify some of the ideas and some of the differences in language and procedure that are associated with making the change from discrete random variables to continuous random variables. The other things I was going to do is just talk about a couple of the homework questions. There was a question on the discussion board about 3.1-4, where you're given the moment generating function of random variable x, and are told that the moment generating function is e to the 5t minus e to the 4t divided by t for values of t not equal to 0, and it's equal to 1 for when t is equal to 0. The question that came up had to do with trying to take derivatives of this moment generating function to find the mean and the variance. And the problem comes in that when we take the derivative of this, remember theoretically we could take the first derivative of the moment generating function and evaluate it at 0, and this is going to give us the mean. And we could take the second derivative of the moment generating function evaluated at 0, and it's going to give us the expected value of x squared. The difficulty of actually doing this is that once you take those derivatives and you try to evaluate them at t equals 0, you get an indeterminate form with 0 over 0. And so you need to use L'Hopital's rule in order to find the mean and variance if you do it that way. The easier way to approach this problem is to recognize that the form of this moment generating function matches up with the form that's given for a moment generating function for a uniform distribution that's given in the textbook. So this is the general form for the moment generating function of a uniform distribution, continuous uniform distribution that's uniform on the interval from A to B. And by uniform, what that means is that the probability density function is equal on that entire interval. So it's from A to B. Should really only be defined here. Pretend that's not there, but it would be constant over this range and then 0 elsewhere. So this matches this format, and so we can use what we know about finding the mean and the variance for a continuous uniform distribution if we recognize that this is taking that form. Because, remember, a moment generating function is associated with a unique distribution. If we know one, we can find the other. So once we recognize that, we can see that our B is taking the value 5, our A is taking the value 4. So in this case, x is uniform on the interval from 4 to 5. And then we can use that fact to find I think it asks us to find the probability density function f of x, the expected value of x, and the variance of x, if I remember properly. And just keep in mind that the probability density function in general for a uniform continuous is going to be 1 over b minus a. The expected value is going to be the sum a plus b divided by 2. And the variance is going to be b minus a squared over 12. And those are just formulas that are shown in the book, and we can derive those if we like to. I can't remember if the book actually derived them or not, but those are the formulas and we can use them if nothing else. And if anybody would like to work on deriving them, they're not really that hard to derive. Okay. Next question I was going to talk about, this one is, I think, definitely a little on the tricky side. It's 3.1-6. This is the one, there's a supermarket selling watermelons, and they're going to have N watermelons to sell. They gain $1. That's what their profit is for each watermelon they sell. And the number of customers that they have who want to buy watermelons is random. So the number X, it takes on a value between 0 and 200. And we're told that we are modeling the distribution of X using a continuous uniform. So over that range would be 1 over 200. Now, one thing I just want to note about this problem is if we really, really think about it, the number of customers who want to buy watermelons is actually not continuous, right? It's countable, right? We can't have 1.37582 customers wanting to buy watermelons, right? It's a discrete, countable thing. But so this is a situation where the authors are asking us to model this using a continuous probability model, when in fact it's a discrete one. And this is something that is commonly done if you have a discrete random variable that takes on many, many possible values. It's often more convenient to model it with a continuous random variable. But I just wanted to mention that in case anybody noticed it and found it a little confusing. So this is a discrete random variable being modeled as if it were continuous. And this can often be helpful, especially in a case where we're going to be trying to maximize something, to have something that's written in terms of an integrable function makes it easier to do that. Okay, so X is the number of customers, and that has this distribution that we're told. We're also told that they feel that they lose $5 for each customer who wants a melon but doesn't get one because they run out, and that they lose 50 cents for each unsold watermelon if they have more than they needed. So the question is, what should N? How many watermelons should they have in order to maximize the profit? So the hint they give us is that if X, so the demand, is less than or equal to the number of watermelons they have, then their profit is they make $1 for every watermelon they sell, and there'll be X of those because they had more melons than demand. And then they'll lose 50 cents for the N minus X watermelons that are left over. So this will be the profit if X is less than N or equal to N. If X is greater than N, then they're going to sell their N watermelons, but they have more people who want them. So they're going to be X minus N extra people who wanted watermelons and didn't get them, and they'll lose $5 for each of those people. So the profit is going to be different depending on if the demand is greater or less than the number of watermelons. So the idea with this problem is to figure out what the expected profit is. And then so we're going to find the expected profit as a function of N. And then we're going to use calculus to figure out the value of N that's going to maximize that function. The key to this is really to breaking your expected value when you calculate the expected profit, to break it up into two pieces. So overall, the expected value of the profit, we're going to integrate over two different pieces and add them together. From 0 up to n, the expected value of the profit is going to be our $1 times x minus 0.5 times n minus x, and we need to multiply that profit that's in that range of values by the probability density function, 1 over 200. We'll integrate with respect to x. And then we also need to look at the profit that would occur for values of x that go from n up to 200. If x is greater than n, remember it can't go to infinity because the most demand they're going to have, x can only go up to 200. That's how they defined their distribution in the first place. So we're going to have the profit in this situation, which is $1 times n, minus $5 times x minus n, and that whole thing is going to get multiplied by the probability density function. If we go through the process and do this integration, we can find the expected value of the profit as a function of x, and then take the first derivative and set it equal to 0, and you'll be able to solve for the value of n that is going to maximize your profit. So kind of work through this idea. But when we have sort of two different profits here, we have to break it up into pieces, and that's really the key to this problem. Okay, and the last of the homework problems that had a question about, probability density function of x is given by f of x is equal to c divided by x squared, where x goes from 1 to infinity. We want to find c such that f of x is a probability density function. The key here is to remember what the conditions are for the probability density function. We know f of x has to be greater than or equal to 0. So clearly, for that to be true, c is going to have to be positive, right? But the other key thing we need is we need that the total area under the curve in this support is going to be equal to 1. So the key here is to integrate over the support from 1 to infinity our f of x, which is c over x squared, with respect to x, set that equal to 1, and we should be able to solve for c. So that's really the key to that problem. And then when we look at the expected value of x, it asks us to show that it's not finite. What we should be doing when we're showing the expected value of x, remember that we are going to be, we've got a constant c, but we're going to be integrating x times c over x squared with respect to x. So what we're going to find is that we have c times the integral from 1 to infinity of dx over x. This is going to be c times the natural log of x, evaluated at 1 and infinity. Remember, when we want to try to evaluate infinity, what we're going to do is we're going to take the limit as n goes to infinity of c times the natural log of n minus c times the natural log of, sorry, this should be 1, not 0. 1, and we need to focus on taking this limit, and if it's not finite, it means that we're going to have something that's not bounded here. So just to kind of, I know sometimes these problems are a little, people are not quite sure how to approach those, but that's really what we want to do when we need to evaluate at a limit of infinity for our integral. We need to take the limit as we go to infinity for that part. All right, so that is what I had to talk about from the discussion board. Any other questions or anything need clarifying? Okay, so we'll be done for today. Thank you.